we have seen how to discretize a complex domain which may be simply connected or multiply connected and break it up into tiles in an unstructured way, and we have also seen a structured way of generating a body fitted grid, so that we can now say that if given a complicated flow geometry, at least for 2 dimensions, we can come up with the interior locations of all the grid nodes in terms of the xi, yj of all the points, such that when you can make control volumes out of it, we can make tiles out of it, and when all the tiles are put together, we have the entire computational domain. And the algorithms that we have discussed are for any arbitrary shape geometries. So this enables us to deal with, we are now at a stage where we can look at the complexity of flow in terms of a turbulent reacting flow, and we are also able to tackle part of the geometrical complexity in terms of generation of the control volumes and the location of these. But there is still one element of the overall solution process that we need to worry about when we come to complex geometries, and this is with regard to the evaluation of the pressure. We have seen that in the case of simple geometry, where we expressed our equations in terms of Cartesian coordinates, and where the overall flow domain fitted into something like a cube type of situation, then we derived an equation for pressure or pressure correction on a staggered grid, where the evaluation of the velocities was staggered in that particular component direction by half a grid point. Therefore, we were doing the discretization of the 4 equations, that is the continuity and the 3 momentum equations, on 4 separate grids. Something like that is quite okay when we have a simple grid, because we can easily translate the plane by half a grid point in each direction, in the x direction for the x momentum, in the y direction by the y momentum equation, and so on. But when you have a complicated domain, we have seen how we generate the grid for a body fitted grid or for an unstructured grid, and these methods are not amenable to for shifting these things by half a grid point like that. So to generate a staggered grid is not so easy, and one could potentially say that we could generate in a body fitted in a structured coordinate system, but we also see that the control volumes are not necessarily rectangular. So that means that all the areas and the surface orientations will change from one grid point to the next half grid point. So that means that we have to store quite a lot of information about each grid point. For example, when we talk about 3 dimensions, we have to know the overall volume, and we have 6 faces. We have to know the face areas, and we also have to know the direction coordinates of that surface normal vector. So there are 6 times 3, that is 18 directions cosines that we have to remember for that particular control volume, in addition to the area of the 6 faces and then the volume of the overall face. So that is 18 plus 6 plus 1, that is about 25 quantities we have to remember for a grid for a single point, for a single node in dealing with a structured grid. And if you now have 4 such grids, so that we can employ a staggered grid system, then the amount of storage associated with the grid itself will become very large. In addition to that, we have the difficulty of generating these things. So the staggered grid approach is not very amenable for computation for a complicated flow geometry. So we have to go from staggered to a collocated arrangement. Collocated arrangement means where all the velocities and all the pressure and temperature turbulent kinetic energy, all these things are evaluated at the same point within the control volume, as opposed to the staggered or non-collocated approach, in which some quantities like pressure and temperature and turbulent kinetic energy, these are evaluated at the center, and the fluxes and the velocities are evaluated on the faces. So we have to come up with a way of adapting the approach for a collocated mesh. It may seem to be very obvious. The major difference comes when we are looking at the evaluation of the pressure. In a simple kind of grid where we have, let us say these are the this is I here and j here, so I plus 1, I minus 1, j plus 1, j minus 1 type, and here we are evaluating the pressure, and typically in a staggered grid we evaluate u here and v here, u here and v here, u u here and then v like this. This is how we evaluate, and when we solve the continuity equation, it is dou u by dou x plus dou v by dou y equal to 0. We take a control volume centered around the point where we evaluate the pressure, and if this is P, by notation we have this point as capital E, this point is capital E here, and capital west, capital north and capital south. These are the 5 points at which pressure is evaluated, and when we take this control volume here and we discretize this, we can write this as UE minus U west divided by delta x plus V north minus V south divided by delta y equal to 0. And this enables us to introduce the velocity correction UE prime and Vn prime like that in terms of the pressure correction, and we therefore evaluate the pressure correction. For example, we write this as UE star, where star indicates the velocity obtained with a guessed pressure field, which is P star, plus UE prime minus UW star plus UW prime divided by delta x plus Vn star plus Vn prime minus Vs star plus Vs prime divided by delta y equal to 0. And we make use of the approximate form of the corresponding momentum equations to say that UE prime is roughly equal to P prime, that is pressure correction at E minus pressure correction at P divided by some delta x with the appropriate units to some geometrical parameters to make this dimensionally consistent. And similarly, Vn prime is approximately equal to P prime north minus P prime P divided by delta y, and so on. We substitute these things here and get an equation for pressure correction, sum of A and B, P prime and B equal to B. So this is how we evaluate the pressure correction, and once we solve this, then we substitute it here to get the velocity correction, and then we can go from a guessed pressure field into a guessed velocity field into a new velocities here and here. So that is a standard way that we discretize the momentum equation on a staggered grid, and thereby enable the determination of pressure which is not linked to density in the case of incompressible flows. So this creates a means of using the pressure as a continuity enforcing method, a continuity enforcing condition. So we can obtain a pressure correction such that the new velocities correction, the new velocities obtained through the velocity corrections that are coming here will satisfy the continuity equation. So that is how we have approached the determination of the velocity field and pressure field in incompressible flows. We have made use of a staggered grid approach. So this meant that you had a grid like this for the pressure, and you had a separate grid for the u velocities, and even a separate grid for the v velocities, and so on. And in the case of 3-dimensional flow, you have 4 grids, one for pressure at ij, velocities at I plus half j k, the v velocities at I j plus half k, and w velocities at I j k plus half. So you have the main grid and then 3 staggered grids like this. When you have a regular grid like this, then it is very easy to see that the areas are roughly the same, or they go in a certain way. For example, when you go to a cylindrical coordinate system, it is very easy to compute the areas and the distances that come about here. But when you have a complicated geometry, then it is not readily clear as to how we can implement something like this. And so the logic that we can use for a structured complicated grid is that one can say that we can do the same thing. We can take a similar control volume, it may be like this, and we can construct a control volume like this. But here what we would like to do is to, instead of using 4 different grids, this is the staggered grid, we would like to use a collocated grid. In which all p, u, v, w are evaluated at the same I comma j comma k. So if you have this kind of a single grid like this in the case of and if you use this to evaluate p, all the quantities at the center of this, then, and if you want to apply, if you want to discretize the continuity equation in order to get the corresponding pressure in this, then we need to have velocities here and u velocities here and here. So we can write it like this, that u, if you say that this is I here and j here, we need u at I plus half j minus u at I minus half j divided by delta x. We will just call this as delta x, it can be slightly more complicated, plus v at I j plus half minus v at I j minus half divided by delta y equal to 0. This is the discretized form of the continuity equation, and in order to apply this we need to have values of the velocities at these phase points, and these are readily available from the momentum equation on a staggered grid, whereas in the case of collocated grid, these values, the velocity values, are not available here, and that is the great advantage of the staggered grid. So we know the velocities only at these points here. So we have to estimate the value of the velocities at the faces from, for example, from these 2 points, and we can estimate, one can say that we can estimate this from these 2 points and this from these 2 points and like this. If we do that, then we can do interpolation. So we can get phase velocities by interpolation. And then we can substitute this in terms of fluctuating quantities and then convert this into pressure correction as in this particular way, and then we can try to finally get an equation for pressure correction like AP equal to B type of thing in this way. But if we do this interpolation, linear interpolation, for example, when we say that what is this value given this value and this value at these distances, we can do a linear interpolation, and the linear interpolation is such that these two distances are the same, then this will be average of these two, and again this will be the average of these two. So if we do that linear interpolation, which will give us a second order estimate for the phase velocity at this point, which is good, then what we find is that this matrix here will not have the value of Pij. Okay, so the value of Pij here is being computed only from these points here without any contribution coming from this. So that means that if you have a grid like this, then this pressure and this pressure will determine this, these four pressures will determine this, and again these four pressures will determine this. So with the result that since this is not coming into picture, if you have, for example, a strange case of 100 100 and 50 50 pressure here, then the pressure gradient which is coming into here, which is into the momentum equation, will be such that the pressure gradient in this direction is 0 and the pressure gradient in this direction is 0, and let us say that you have one here and one here. So in that sense one can come up with a pressure variation like this, which is strongly varying between 101 101 101 like this, which is seen by the flow as if it is a uniform pressure, because the pressure gradient is being determined by 2 points by skipping this particular point, and this is 100 and this is 100, so it is uniform, so that the flow will not react to the fact that you have these very rapid variations of pressure. So that a pressure variation such as this, okay, 101 101 101, similarly 51 51 like this, is seen as a uniform pressure field. Okay, so this is seen as uniform pressure field, and therefore there is no corrective action to smoothen this pressure variation, to get rid of this very high frequency pressure variations, and this gives rise to what are known as checkerboard oscillations. Of the velocity field and pressure field like that, which will be difficult to get rid of, because this is seen as an equivalent uniform pressure field, and this can play havoc with the solution. And although one can see that there is obviously something wrong with this, one cannot do anything about it. The flow will converge, the solution will converge towards this. And these checkerboard oscillations can be shown to be associated with this linear interpolation. But when you use the staggered grid approach, we can see here that the pressure at the central point here is strongly influencing the pressure variation at this particular point. The discretized momentum equation at point P, discretized continuity equation at point P, which determines the value of pressure, has a component of 4 here, weightage of 4, and this is weightage of 1 from all these points here. So from that point of view, there is a strong say of the pressure at this point, and if you have something like 100 like this, then immediately it will see that there is something wrong, and that kind of linkage, okay, that kind of mechanism to eliminate these non-physical high frequency small wavelength pressure variations, that corrective action is not there when we go for the staggered approach with the linear interpolation to get the phase velocities which are required in the discretization of the momentum equations. So it is, the problem is that the discretization continuity equation. So when we want to discretize the continuity equation at the center of the cell, we need the phase velocities, and these phase velocities are obtained from the discretization of the momentum equation at about the same point. Therefore effectively the pressure evaluation at a particular point gets decoupled from the velocity equation at that particular point, and this gives rise to the checkerboard oscillations, and this is a well known problem with solution at the collocated grid, and this can be readily avoided by using a staggered grid approach. But while the staggered grid approach is readily implementable for a structured simple grid like this, when you are looking at a complicated flow domain where you have the grid lines curve around bodies of arbitrary shape, in such a case staggered grid approach is not possible. We must use a collocated grid. So this is where Ree and Chow, there have been the general attempt to deal with this checkerboard oscillations is to introduce a fourth order term in the pressure equation to suppress these things, and that particular approach has been formalized by Ree and Chow who suggested that the phase velocity here is obtained by the interpolated phase velocity. So that is what right now here, if you want to say that you want to get the u velocity here, then this is this plus this divided by 2, assuming that these are equidistant. So that this velocity plus this velocity divided by 2 is the interpolated phase velocity minus the some contribution of the d which is coming in this here. D is essentially multiplication of this times the gradient of pressure which is coming in the momentum equations, and they suggested that this gradient of pressure is also interpolatable, and this is broken up into two parts. This is the gradient of pressure when completely interpolated, and this is a contribution with the interpolated value of the coefficient, and this is the gradient evaluated at that particular I plus half j. Let us say this is I plus half j. Okay, so this is the interpolated pressure gradient source term which is coming in the evaluation of the momentum equations. Okay, evaluation of the momentum at this point and this point, and this is the pressure gradient evaluated at this half point here. So which we can write as, so this is the interpolated velocity, phase velocity I plus half j minus some d here, interpolated thing. This pressure gradient here at this point is this velocity, this pressure minus this pressure divided by 2. So that we can say is P minus Pe divided by delta x, minus this interpolated term. And what this means is that this can be shown to be equivalent to a fourth order correction in terms of the pressure gradient here. And what we note is that in cases where you have a smooth variation of pressure, instead of a thing like this, it is varying smoothly like this, then this additional correction is almost 0. Where you have this strong variation, then this is bringing in the value of pressure at this point in the evaluation of this. So with this additional correction to this, we can introduce a correction to the treatment of this sort of rapidly varying pressure gradient as a uniform pressure gradient. So essentially what the Richow have proposed is that the determination of the phase velocity, okay, at the points where the velocity is not being determined, velocity is being determined only at these 2 points, but we need the phase velocity here in order to substitute into the equation here. So they made this phase velocity determination sensitive to the pressure gradient between 2 successive points, and that sensitivity is introduced into this term here, and the correction that is coming out here will be almost equal to 0 when you have a smooth variation of pressure, but this will be the dominant correction, dominant contributing factor to making this uniform in the case of a strongly varying pressure field. So with this Richow interpolation method to determine the phase velocities, okay, where the phase velocity is partly determined by the interpolated component or the velocity here, and partly by the difference between the interpolated pressure gradient and the actual pressure gradient at that point, okay, is what this one is. So that difference will be 0 if you have a linear variation of pressure. If you have smooth variation of pressure, that difference will be a second order effect, but if you have a strong variation of pressure as in the checkerboard oscillation, that pressure will dominate. So this approach has made it possible to use a collocated grid for for a structured grid approach, and so this has really enabled the extension of the simple type of calculation procedures to a body fitted grid system, because in these systems it is possible only to use a collocated approach and not the staggered approach. So this was proposed in early 1980s, 81, and this was immediately adopted by large number of people, and this has proved to be a very successful approach to the cure of the checkerboard oscillations that are found in a collocated grid system. One has to see this in the general context of trying to make the pressure evaluation sensitive to the smallest variation that is possible, that is across 2 neighboring points, and that is what this is bringing. And this sensitivity here is put in such a way that that sensitivity will, that additional term will be almost 0 when you have a smooth variation of pressure, when you do not have this checkerboard oscillations. So the overall accuracy of the computation is not affected, but it is a specific cure directed at strong variation, strong and local variation of pressure. With this approach, when we add this to the overall determination of pressure in the context of determining AP prime equal to B type of solution with interpolated plus pressure corrected phase velocities, then it will lead us to an equation for AP prime equal to B, which can be solved along with the discretized momentum equations to give us the pressure and velocities at the same point, they are collocated, and this type of with this type of approach one can very in a fairly straightforward way one can use a body fitted grid for the calculation of the velocities. Without this kind of cure it will be very difficult to avoid a checkerboard oscillation. So this is a modification that is required when we are planning to use a collocated grid approach, which is the norm for complex flows. Now the question is, we understand how this can be done, at least in we can guess it how this can be done for the case of structured grids. Now what do we do for the case of unstructured grids? Because even in unstructured grids one can face the same problem of having to determine the phase velocities, and one has to also understand how we can extend this. Actually the extension of this Riccio interpolation algorithm for the determination of the phase velocities is relatively straightforward in the case of unstructured meshes, and the very similar approach to this can be used. And let us just look at one specific case in essentially symbolic terms. So let us consider an unstructured thing like this. We have been too rash like this, and we are concentrating on this particular cell given by these 4 nodes, and we have the neighboring nodes n1, n2, n3 and n4. These are the nodes at which correspond to the centroids of the neighboring nodes which are sharing a particular phase with this particular thing. Okay, so we have flux across this phase, flux across this phase, flux across this phase, and contribution of flux which is coming into this, and this represents this net flux which is coming into the control volume from the neighboring cells based on the values of the variables at these nodes will determine the rate of change of that particular variable in that particular cell. So we can write considering steady equation, we have del dot rho u phi equal to del dot plus q as the standard governing equation which is valid at every point, and then we integrate this over the volume of this particular cell in order to derive the conservation equation applicable for this particular cell in the unstructured finite volume method. And making use of so we have diffusive flux here and convective flux here, and we can bring these two together, and then we can make use of the Gauss's divergence theorem to express this as a surface integral dotted with S over the closed surface S is equal to Q dV over the volume here, and this will be discretized, this will be evaluated on each of these faces, and which we can represent in this form, where f is the neighboring, okay, let us say that small f is the neighboring face of q times omega. Okay, so we are making a discrete evaluation of the fluxes over the face of the neighboring faces of the point P here. So this is a neighboring face, this is a neighboring face, this is a neighboring face, like this, and we have the evaluation of the convective flux and the diffusive flux, for example using the upwind scheme and then the central scheme for these things, multiplied dot producted with the surface area of each face, like this. So this is the finite volume approximation here, and by using the appropriate approximations and all these things, this can be converted into an overall equation like this, AP phi p, where phi is the value of the variable at the point P here. This can be converted into an algebraic equation like this, AF phi f, where f is the neighboring point to P. So that is n1, n2, n3, n4. So the value of the variable at the neighboring point, at the neighboring node, which is denoted by capital F. Here the face is denoted, neighboring face is denoted by the small f, and this is the capital F here, equal to some BP. So this is the overall equation that we can come up with, and we can also put it in for the use of our convenience here as sigma neighboring points over a neighboring point divided by AP phi f equal to BP divided by AP. Okay, so this is the equation which determines the value of the variable at a particular point P in terms of the neighboring points, and also in terms of BP, which represents source terms and other kind of things. So this also determines the values of the various velocity components. Okay, so when we apply this method for the various velocity for the momentum equations, we generally treat the pressure term as an additional source term. So in such a case, we can write UP here plus A and BP by AP UF sum over all F, which are the neighboring points of P, equal to some BP corresponding to this minus dP gradient of P at point P, where your dP is related to the phase volume divided by phase fluxes. No, this is the phase volume, this omega P here, divided by this AP term here. So essentially you have the contribution of terms other than the pressure gradient coming into BP here, and the velocity at the neighboring points here, and the pressure gradient evaluated at this. So this is a treatment of the discretization of the momentum equation, which will ultimately be converted into that AV equal to B, from which we get V. U at every point. Okay, so this is the approach that we can use to discretize the momentum equations and convert them into an algebraic type of equation for a given point. Now the question is, how do we solve the continuity equation? Because we still need, in order to solve this, we need to solve the we need to know the pressure. So this is where we follow the simple type of approach, where we have P star as a guessed pressure field, and once we have the guessed pressure field, this can be converted into an equation which will give us the starred velocity field. So we can say that we can follow the same procedure, and you can write UP star plus sum of okay, we can call this whole thing as some AF UF star equal to some BP minus dP times gradient of P star at P. So this equation with the guessed pressure field here will give us the velocity at the node here. Now when we want to discretize the continuity equation here, we need the phase velocities. Okay, so it is the obtaining the phase velocities by simple linear interpolation. Okay, if you want the phase velocities here, you take these 2 points, which is what we get in terms of UP star, and based on that one can get a phase velocity here. But that linear interpolation will give rise to checkerboard oscillations. So we'd like to implement a similar kind of reach-out correction to onto this unstructured mesh, so as to come up with the interpolation scheme for the phase velocities. So what we'd like to do is that, like in the previous case, we know that this is the correct expression, that is the final velocity field with the correct pressure field will satisfy this discretized equation. It's only the approximate pressure field will give rise to the approximate velocity field as per this, and we can subtract this from this and derive the expression for the velocity correction as okay. So this is the pressure velocity correction, and in the simple scheme, for example, we neglect this. Okay, so this equation is also applicable at the faces. So we can say that we'd like to have what we want to have is an estimate for the velocity corrections here. Okay, so we need to have a proper interpolated velocity of the velocity at the face value. Okay, so we could write this as Vf prime, the interpolated velocity correction corresponding to a pressure correction, as the interpolated velocity correction based on the velocity corrections at P and N1, N2, N3, N4, okay, minus d phase times gradient of P prime at the face minus the interpolated gradient at the face. So this way of writing is similar to writing it like this. So we have the interpolated velocity here, that is the interpolated velocity. We are now directly writing the expression for the velocity correction. So you have interpolated velocity correction. For example, this can be if you are considering this phase here, this will be Vp times, if you say that this is x1 and this is x2, or L1 and L2 here. So for phi f corresponding to this here, interpolated will be given as phi p times L1 plus phi n3 times L2 divided by L1 plus L2. So in this way we can get linearly interpolated value of phi at this particular phase depending on the distance here and the distance here and the value here and the value here. So this value here is the velocity correction obtained from this type of interpolation. This pressure gradient interpolated thing at the phase value at the corresponding phase is also the interpolated thing based on the pressure gradient term coming into the momentum equation, and this particular one is the pressure gradient which is coming at the phase value. Okay, so this will be evaluated as this minus this divided by this distance. So this is the interpolated velocity. And this is the interpolated pressure gradient term. Okay, from P and F. Okay, so that is the variable values, corresponding variable values at P here, and capital F which represents the node locations, and this is also from capital P and capital F values, the interpolation, and this is a value which is actually based on this immediate things like Pp minus Pe. So for example, if if you are looking at this phase here, this gradient of pressure correction at this particular point here will be given by pressure correction at P minus pressure correction at N3 divided by that distance delta x. Okay, the appropriate distance corresponding to this thing. So in this way, in the evaluation of the velocity correction, we are bringing in not only the contribution from the interpolated thing, but also the pressure gradient associated with the pressure corrections at that same point here, okay, at corresponding to the pressure correction at that node. So the pressure correction at that node is coming into the evaluation of the velocity corrections, and that is precisely what we are doing here in the Ryczew algorithm. So by evaluating this for each of the phases, we can bring in the contribution coming from the pressure fluctuation at this node in addition to the contribution coming from the interpolated values. And again, as we said here, in the case where the pressure variation is smooth, this term will be almost equal to 0. Okay. And what we are left with is the velocity correction obtained from the interpolated velocities only. So that is how it is. So when you do not have any threat of checkerboard oscillations, then the phase, the correction to the velocity at the particular phase from the interpolated one is as good as the correct velocity. But where you have severe variation of the pressure correction, this will tend to suppress those oscillations. So in this way, the extension of the Ryczew method for for the interpolation of the phase velocities can be readily done in the case of structured meshes in almost identical way in this particular fashion, and this can be incorporated into these interpolated velocities can be incorporated to discretize the continuity equation, and from which we can obtain the pressure correction equation. So pressure correction equation is obtained from estimated velocity at all phases. So this is done at each phase. If you have 4 phases, we will do it for 4 phases. For this particular volume, we will be getting one here, and one here for the 3 phases. So in that sense, this can be applied. This discretization is applicable for any number of phases, and same way the estimation of the phase velocity is also applicable for any number of phases, and together we can estimate all the velocity fluxes through each of the phases and determine the pressure correction contribution coming from that velocity contribution, and thereby we can extend this. So this method is in this way we can make use of the collocated mesh approach for the determination of the pressures, and this approach has been very widely used for unstructured formulations, and once we do this, the simultaneous solution of the momentum equations along with the continuity equation does not pose any additional problems, and we can avoid checkerboard oscillations. And once we do that, we can deal with a single grid, and we can get an overall solution. So in this way, one can see that when we are dealing with complicated flows with respect to geometry, we can represent the geometry either in a structured body fitted grid or in an unstructured meshes, and we can adopt more or less the same procedure to convert a given partial differential equation into a discretized algebraic equation like this, and then convert this into that a phi equal to b and go through the overall solution process, and we can solve any number of equations including for turbulent kinetic energy and all those things, and in the evaluation of pressure we have to use the collocated approach correction proposed by Rie and Chow. Rie and Chow is just one of the popular ways of dealing with the checkerboard oscillations, and many other corrections are also possible. All of them will are some extensions and some equivalences of introducing a damping term with related to pressure variation in the immediate thing with respect to the interpolated pressure variation. So with this one can claim that we have an overall solution procedure for dealing with an arbitrarily complicated physical flow as long as we have say a Newtonian fluid, and arbitrarily complicated geometrical features. Although we can claim this, there are lots more details that one has to work out before one can go into the full evaluation. A lot of care is needed, and a lot of diligence and meticulousness and bookkeeping and smart programming, all these things are needed for a successful implementation of the principles that we have discussed into an algorithm and a computer program which will enable us to calculate the flow field. We have discussed the principles, and I hope you have benefited from this.